Section 5.1. These notes are rather wordy, so I would not expect you to write down everything word for word. So Rutherford's model of the nucleus and the rest of the atom being empty space explained some properties of atoms, but it did not explain chemical properties. So scientists were looking for a new way to explain what was going on. It did not explain why something would glow and give off light when it was heated, for example, like in the flame test lab that we did today. So we were looking for a reason why. So in 1913, a scientist by the name of Niels Bohr, who was actually a student of Rutherford, developed a new model. He changed Rutherford's model, and it incorporated these discoveries about atoms that giving off, absorbing, and emitting light. The key part to Bohr's model is that electrons were only found in specific paths or orbits around the nucleus. So here you had the nucleus with protons and neutrons, and then Bohr said that there were paths or orbits around the nucleus where you would find the different electrons. And this is what we would call the Bohr model. He also said that each electron orbit has a fixed amount of energy, and these fixed energies are called energy levels. And the amount of energy needed to move an electron from one level to another is called a quantum. It's like a little minimum amount of energy. We can't have anything in between. A good way to think about these energy levels and the quantum of energy that we have are looking at a ladder. So thinking about a ladder, you can't stand in between the rungs. So the same thing, electrons in an atom cannot be between energy levels. So each rung of the ladder is a different energy level in the atom. In order to get from one energy level to the next, the amount of energy that's required is what we would call the quantum of energy. And in this ladder, though, it is kind of unusual. The rungs are unequally spaced. Just like in the atom, the energy levels are not equally energy spaced, and higher energy levels are closer together. And to get from one energy level to the next, then we give it a quantum of energy. And then whenever that electron goes back down to the original energy level, it emits the photon of light, like we saw in the lab today. So comparing Bohr to Rutherford, the Rutherford model did not explain elements, why elements that were heated gave off light, and the Bohr model explained that with energy levels. And like with many models, it does not the Bohr model does not explain things perfectly. So we're looking for a little bit more information and more details, and that's where the Schrödinger comes in. Erwin Schrödinger used very complex mathematical equations to explain where electrons were, in the atom. And his description of the atom is what we're used today, and it is called the quantum mechanical model. And it comes from the mathematical solutions to the Schrödinger equation. So there are similarities in the Bohr model to the quantum mechanical model, in that we have certain energy values or energy levels of the electrons. However, we do not have these circular orbits for a specific path for the electron to take. So the quantum mechanical model tells us the energy that an electron is allowed to have and where it is likely to be found in various locations around the nucleus. In the current quantum mechanical model, we talk about where we find an electron in terms of an electron cloud. And it is the region around the nucleus where you can find the electron, and it's more like a fuzzy cloud, and the it's more dense, where we have a high probability of finding an electron. So it's more of a blurry region, no defined set locations. So the Bohr model and the quantum mechanical model, kind of compare them just for a minute. The quantum mechanical model and the Bohr model both restrict the energy of electrons to certain values. And however, the quantum mechanical model does not give us an exact path for the electron around the nucleus. And let's get into that a little more. And in the Schrodinger equation, we not only do we have a certain energy level where we could find an electron, but we also come up with what we call an atomic orbital. An atomic orbital is the region of space where we have a high probability of finding an electron. And it's actually a 3D image or a three-dimensional location where you find each electron based on the amount of energy that they have. Each energy level in this model is labeled, and the first thing we label is called the principal quantum number. And these are like the main energy levels. So there's the first main energy level, the second main energy level, third, and fourth, up to about 7 main energy level. For each main or principal energy level, there are several orbitals with different shapes and different amounts of energy. And these different shapes within the principal or main energy level make up what we call sublevels. So there's like the main level, which is the principal, and then there are sublevels where we find the orbitals as well. So each energy sublevel gives us one or more orbitals of different shapes, and within these orbitals is where we find the electrons. There are different orbitals based on their different amounts of energy and which main level they're found in. And so the first type of orbital is an S, and it is what we call, it's spherical, it's just round. There are p orbitals. The p orbitals are dumbbell shaped, but they're 1, 2 little kind of nodes, and both of these little nodes are part of the orbital itself. There are 3 p orbitals within this within its sublevel, 1, 2, 3, and you can see they're oriented in different ways around the XYZ axis. Their next sublevel is the d sublevel, and there are 5 d orbitals, and you can see that they have a kind of 4, almost a clover shape, oriented in 4 different locations in space, and then the 5th one looks just really funky. The 5d orbitals again have different orientations in space, even though 4 of them have the same shape. So here's a summary of the different main levels and how many sublevels and so on. So the principal or main energy level, so the first energy level has 1 sublevel. The type of sublevel is we name it 1s, and it has 1 orbital, which is that circular shape, and each orbital can hold 2 electrons, so a maximum of 2 electrons. In the second main or principal energy level, we have 2 sublevels. We have one that we name 2s and one that we name 2p. The 2 represents which main level it belongs to. So the 2s and the 2p, the p sublevel having 3 orbitals, that's 4 orbitals total, having 8 electrons in the second principal or main energy level. In the third energy level, we have 3 sublevels. We name them 3s, 3p, and 3d. A 3s, an s sublevel has 1 orbital, a p sublevel has 3 orbitals, a d sublevel has 5 orbitals. That makes 9 orbitals total at 2 electrons each for 18 electrons. The fourth main energy level has 4 sublevels, and we get the 4s, the 4p, the 4d, and also we add the 4f. An F sublevel has 7 orbitals. We're not going to talk about the shape of those because it gets really crazy. But total, with all those orbitals together, that's 16 orbitals. We get 32 electrons in this fourth main energy level. As you may have figured out from that chart, the principal quantum number, or the main energy level, always equals the number of sublevels that it contains. So, and then also the number of orbitals is equal to the energy level squared. The total number of electrons that any orbital can have is 2. It's like a 2-seater, can't fit any more people in there. And the maximum number then of electrons that any principal or main energy level can have is 2n squared. But that I'm not really too worried about. Tomorrow we'll be working on how each electron goes into its main energy level, sublevel, and orbitals.